good review of the Institute for Advanced Study. You were telling us about 2+1-Dimensional gravity.
Thank you. The most important thing to tell you about this talk is that I'm not at all sure what I'm going to be saying is correct. I considered whether it was therefore my duty to cancel the lecture. It was tempting. But I justified giving the talk to myself on the grounds that you might learn something from what I was trying to do, even if it turns out that my proposal isn't right. So we're going to be talking about three-dimensional pure quantum gravity with the Einstein-Hilbert action that I've written in terms of Newton's constant and the cosmological constant, which has been written as 2 over L squared. And it's a very tempting problem to study because three-dimensional gravity classically is said to be trivial. Nothing happens. The Einstein equations imply that depending on the sign of the cosmological constant, every solution is locally equivalent to either de Sitter space, Minkowski space, or anti-de Sitter space, depending on whether L squared is positive, negative, or 0. So since it's trivial classically, it's reasonable to hope that you at least might be able to solve it quantum mechanically. And maybe you'd be able to learn something from the exact solution. So it's been studied from many points of view by people who hoped to, in this way, get a soluble model of quantum gravity, but nevertheless, the status is fundamentally unclear. Now, the main reason that I've chosen to look at this problem again is something called the BTZ black hole, Banados, Teitelboim, and Zanelli, introduced in around 1992. When the cosmological constant is negative, there are black holes in 2+1 dimensions, not when it's 0 or positive. Now, since pure gravity in 2+1 dimensions is trivial, meaning that it has no propagating modes, no gravitons, we might hope that we could solve it, and thereby get an exact description of a quantum theory with black holes. In 4 dimensions, it's hopeless to get a precise description of quantum mechanics with a black hole because the 4-dimensional phenomena are far too complicated. But in 3 dimensions, you could at least possibly get a precise black hole model. Now, you might also conceivably do it in 1+1 dimensions, but 1+1 dimensions is less realistic because the black hole horizon only consists of 2 points. And the basic property of the Bekenstein-Hawking entropy that's proportional to the area or perimeter of the horizon is lost in 1+1 dimensions. In 2+1 dimensions, there are black holes that are like holes in 2-dimensional space. They have a perimeter, and they have a Bekenstein-Hawking entropy proportional to the length of the perimeter. So it's a much more realistic model for black holes, if you could solve it. Now, the first observation, well, the 0th observation about this theory is that by power counting it's unrenormalizable because Newton's constant has dimensions of length in 3 dimensions, a negative power of mass. So by power counting, this is an unrenormalizable theory. However, in perturbation theory, it's actually finite, modulo field redefinition and a renormalization of the cosmological constant. That's so for the same reason that the theory is trivial. After all, it should feel funny to claim that a trivial theory is unrenormalizable. In 2+1 dimensions, the Riemann tensor can be expressed in terms of the Ricci tensor, which in turn, using Einstein's equations, can be expressed in terms of the metric tensor. These are the steps that are used to prove that the theory is trivial. So finally, on shell, the only possible counterterm is the volume of spacetime, that is a renormalization of the cosmological constant. What I've just said is true no matter how you do perturbation theory, but there's actually a natural formulation in which no normalization or field redefinition is needed. This comes from the fact that classically, 2+1 dimensional gravity can be expressed in terms of gauge theory. The spin connection omega is an SO21 gauge field. And it can be combined with the Vierbein E to make a gauge field of a group SO22 if the cosmological constant is negative. There's a similar story if the cosmological constant is 0 or positive. You just combine omega and E into a 4x4 matrix where there's a 3x3 block and E is in the last row and column. And then a small calculation shows that as long as the Theitelboim is invertible, the usual transformations under local Lorentz transformations and diffeomorphisms combine together as gauge transformations of A. What I've said so far is true in any dimension, but there's something crucial which is only true in 3 dimensions. What's special in 2 plus 1 or 3 dimensions is that not only can you combine the fields and the gauge symmetries into gauge transformations of a gauge field A, but you can also write the Einstein-Hilbert action in a gauge invariant form as a Chern Simons interaction, where trace is a certain invariant quadratic form on the Lie algebra, not the obvious one. Now, in the Chern Simons description, the coupling constant has suddenly become dimensionless. The unnormalizability has disappeared back here. Actually, I left it out, but there's a 1 over L in this formula. So the bad dimensional analysis disappeared in the change of variables. And now, it's a superficially renormalizable theory, but it's not just renormalizable, it's actually finite in perturbation theory, since there are no possible local counterterms. In general, in quantum field theory, infinities have to do with gauge invariant local counterterms, but in Chern Simons gauge theory, there aren't any. One way to say it is that since the field equations are that the curvature vanishes, any local counterterm is 0. So classically, we can re-express three-dimensional gravity in terms of gauge theory. Now, quantum mechanically, it's not totally clear that this is valid because we assume the Theitelboim to be invertible, and it's not totally clear we're allowed to assume that classically. But this transformation was valid classically, and therefore it's valid in perturbation theory, because perturbation theory is infinitesimally close to the classical description. Perturbation theory won't take us out of the classical region where the Theitelboim is invertible. But non-perturbatively, there's a real question. As in gauge theory, we'll have to allow the Theitelboim to not be invertible. My own view when I first worked on this was that the gauge theory description was correct non-perturbatively, and one had to allow a degenerate Theitelboim to make sense of the quantum theory. That still might be correct, but it's been criticized fairly convincingly, although I don't really want to go into the arguments. But although there are a variety of technical objections, there's something that to me is a more serious problem with the claim that gravity equals gauge theory non-perturbatively in 3 dimensions. And this has to do with something I already told you about, the BTZ black hole. At some point, it was appreciated that for the case of negative cosmological constant, there's a black hole in this supposedly trivial theory. And that actually makes the theory much more interesting. I think that the main reason it's interesting to try to solve it is, as I said before, that you could possibly get a model of quantum black holes. And moreover, subsequent developments involving the correspondence between anti-de Sitter space and conformal field theory made it clear that the BTZ black hole should be taken seriously. Now, as I actually already mentioned, the BTZ black hole has a horizon of positive circumference and a corresponding Bekenstein-Hawking entropy proportional to the circumference. And therefore, if there is a quantum theory corresponding to pure 3-dimensional gravity, it ought to have a huge degeneracy of black hole states. And in my opinion, we're not going to get them in a reasonable way from topological field theory, though some attempts have been made. And in fact, there's a substantial community of people who are very enthusiastic about trying to do it. But it looks like an uphill battle. Now, before going on, let's discuss what we're going to aim for in trying to solve 3-dimensional gravity. What would it mean to succeed? Well, first of all, we're only going to consider the case of negative cosmological constant. Well, there's some suspicion that quantum gravity with positive lambda doesn't exist non-perturbatively. One reason for this is that it doesn't appear possible with positive lambda to define precise observables. So there aren't local operators in quantum gravity in general, because the fluctuations in space-time mean that the x that would appear as the argument of a local operator, 5x, isn't gauge invariant. So observables in quantum gravity always have to do with some consideration of the asymptotic behavior. And with positive cosmological constant, there's nothing really nice. I'm not sure it's true that, a possible physical interpretation is that a world with positive cosmological constant, such as perhaps the real universe, is always unstable. If that's so, then it would not make sense as an exact theory in its own right, but would have to be studied as part of a larger system, like an unstable particle, like a W boson, which precisely because it's unstable only makes sense in the context of a bigger theory. I don't know whether that's the right interpretation, but in any event, since I don't know any precise observables, I can't try to solve 2+1-dimensional gravity with positive lambda, since I wouldn't know what to try to compute. I can't say it definitely doesn't make sense. I only can say that nobody has convincingly explained what you should aim to compute and thus what it would mean to solve it. And since we don't know what it would mean to solve it, we won't try. This is an advance compared to 20 years ago. 20 years ago, the status of quantum gravity was equally murky for positive or negative cosmological constant. And nobody would have said, I'm going to focus on the negative case because the meaning is clear-cut, and I'll leave aside the positive case because its meaning is murky. So there has been some progress. Now, of course, zero cosmological constant is the borderline, and above 2+1 dimensions, it has a meaningful observable, which is the S matrix. That doesn't really work in 2+1 dimensions. There are no gravitational waves, so without matter fields, in pure gravity, there also are no black holes when the cosmological constant is zero, so there's nothing that could be scattered, and therefore there's no S matrix. And again, there's no clear picture of what you would mean by trying to solve the theory. So we'll leave aside the case of zero cosmological constant. But with negative cosmological constant, we know exactly what we want to do. We want to describe the dual conformal field theory. It captures the asymptotic information analogous to the S matrix when lambda is zero, but it's much, much richer than the S matrix. The S matrix is a kind of poor cousin. Not only does the dual conformal field theory make sense in 2+1 dimensions, but 2+1 dimensions is the case for some of the richest known examples. And one of the precursors of the ADS-CFT correspondence was the work of Brown and Hanau on 2+1-dimensional gravity. They consider 2+1-dimensional gravity, perhaps with additional matter fields. In their analysis, it isn't important to have pure gravity. And they showed that it has an action of a left and right moving pair of Virasoro algebras with C left and C right given by their formula. Well, invariance under the Virasoro algebra is part of the structure of conformal field theory, but there's much more to conformal field theory. So from a modern point of view, what they're describing is part of the correspondence of the bulk theory with a conformal field theory on the boundary. So we can simply say what it means to solve the theory for negative lambda. What it means to solve it is to find the dual conformal field theory. And to repeat, we focus on the case where lambda is negative because that's the only case in which we know what it would mean to solve the theory. Now, this formulation makes obvious a statement that from a classical point of view looks rather surprising. When we look at the classical action, it appears that L, which is the cosmological constant essentially in Planck units, is a free parameter. But the formula for the central charge shows that this must be wrong. According to the Zamolodchikov C theorem, in any continuously variable family of conformal field theories in 1+1 dimensions, the central charge C is a constant. Hence, it cannot depend on a variable parameter such as L over G. It must be that 2+1-dimensional quantum gravity makes sense at most only for certain values of L over G. Of course, there's an important technical assumption in Zamolodchikov's theorem. The theory must have a normalizable and SL2 invariant ground state. This assumption is valid in 2+1-dimensional gravity, with the anti-de Sitter space being the classical approximation to the relevant quantum state. Now, incidentally, the remark that L over G can't be continuously varied isn't special to pure gravity. It holds in any theory of 2+1-dimensional gravity plus matter that leads to an anti-de Sitter vacuum. For example, in the string theory models whose CFT duals are known, L over G is expressed in terms of integer-valued fluxes, which gives a direct explanation of why it can't be continuously varied. It's determined in terms of integers. So we're only going to aim to solve the theory for negative cosmological constant, and even then only for certain values of L over G. But what are the right values? Actually, until here, I think everything I've said is true. It's past this point that it's past this point where I offer no assurances. Well, I don't have any honest way to determine the right values of L over G, but there's a simple picture that gives us a plausible heuristic way to calculate L over G, and it turns out that it gives interesting values. We're just going to take at face value the gauge theory description of 2+1-dimensional gravity, although we don't really know why we should do this, since we don't trust it non-perturbatively, since it doesn't describe the black holes, as far as I understand. Now, in doing this, though, we'll generalize the theory a little bit. In addition to L over G, there's a second dimensionless parameter, since you can add to the action a multiple of the Chern Simons invariant of the spin connection, where here k is an integer for topological reasons. So our problem of pure gravity depends on two parameters, L over G and k, and we're trying to solve a classically trivial theory that depends on two parameters. And we understand that the second parameter is an integer. That has to do with, well, classical considerations. The Chern Simons action is multi-valued. And in quantum mechanics, the action has to be defined modulo 2 pi. And when you implement that, the 4 pi here was chosen, so that if k is an integer, then the action is defined mod 2 pi. Well, so k is a Chern Simons coupling, but in the gauge theory approach to gravity, L over G is a Chern Simons coupling also. So we already understand that k is quantized, and we're just going to quantize L over G by interpreting it as another Chern Simons coupling, just like k. So remember, in the gauge theory interpretation, the gauge group was SO22, but in 4 dimensions, well, this 2 is really the number of space dimensions. So in 3+1 dimensions, it would have been SO32. Precisely because there are 2 space dimensions, we have the fact that SO22 is a product of 2 SO21s. And the 2 SO21 gauge fields, I'll call them A plus and minus, or omega plus or minus E. And the action is a sum of 2 Chern Simons actions, one for A minus and one for A plus. And if we take the gauge theory description at face value, then both k left and k right are integer values for topological reasons. To make sure that the action is well-defined mod 2 pi, k left and k right must be integers. Now, there's something funny happening here, because in general relativity, it seemed that the Einstein-Hilbert action is well-defined, not just well-defined mod 2 pi. By going to gauge theory, we're allowing additional non-classical configurations where the Vierbein isn't invertible. And in that bigger world, the Einstein-Hilbert action is not well-defined as a real number. It's well-defined mod 2 pi if we normalize it properly. So what we've done to determine the right values of L over G, I can't guarantee it's correct, but what we did was we used the gauge theory description to allow some non-classical configurations. And in that bigger world, the Einstein-Hilbert action wasn't well-defined as a real function, but it's well-defined mod 2 pi if we quantize the coupling. As I say, I can't promise it's the right thing to do, but I do believe that if 2+1-dimensional gravity does make sense as a quantum theory, there's some analogous quantization of some kind that is needed. Anyway, if we take the gauge theory description literally, then both k left and k right are integers. And from the formulas of Brown and Hanau and the mapping between gravity and Chern Simons theory, we can calculate the central charges, and their multiples 24 times integers. That's an interesting result because holomorphic factorization is possible in two-dimensional conformal field theory precisely at these values of C. Holomorphic factorization is a drastic simplification. A generic conformal field theory is a many-body system that you can't really solve. There are integrable theories that are much simpler than generic ones, but the holomorphically factorized theories are the simplest of all by far. So we're going to make the most optimistic assumption of assuming that these are the right values of C, or equivalently of K, and that the theory is holomorphically factorized. Holomorphically factorized means that there are left-moving modes. Remember, the dual conformal field theory is in two dimensions, one space, one time. Conformal invariance means that all modes travel at the speed of light. Along the line, they travel either to the left or to the right. And holomorphic factorization simply means that left-moving and right-moving modes don't scatter each other. In general, conformal invariance would allow extremely complicated phase shifts, extremely complicated deformations of left and right moving waves by each other. It's very difficult to describe. So in continuing, we're going to assume holomorphic factorization. That is, we'll assume that there's a theory of left-moving waves and a separate theory of right-moving waves. They don't interact with each other, and we'll just try to describe one of them. That's a drastic simplification because we're now in one dimension instead of two. Or in Euclidean space, because our functions will now be holomorphic. So we'll just try to describe the holomorphic part of the theory, a holomorphic conformal field theory with central charge 24k for some integer k. Now, one simple fact is that the ground state of such a theory is minus c over 24, which is minus k. And that's actually the simplest way to see that c should be divisible by 24 for holomorphic factorization. The ground state energy has to be an integer if the left movers by themselves should be a good modular invariant theory. But it actually is minus c over 24, so we want c over 24 to be an integer. So it was kind of nice when we got this 24 by computing the central charge, but there was a little bit of sleight of hand involved. I won't try to explain it now, but if you wish, you can look in the paper. Okay, well, the ground state has energy minus k. What else is there apart from the ground state? Well, naively speaking, nothing, because 2+1-dimensional gravity is trivial. But that isn't right. At least there are boundary excitations that lead to the Virasoro algebra of Brown and Hanau. Now, if there were no other excitations, the partition function in genus 1 would be this thing. The partition function is defined as the trace of q to the h. So it's the sum over all energy levels. Let's say an energy level n, the number of levels of that energy times q to the n. Q is taken to be less than 1 so that the sum converges. So the ground state had energy minus k, so its contribution is q to the minus k. But according to Brown and Hanau, there's a Virasoro algebra, and we can act on the ground state with the Virasoro generators. So we can make more general states, for example, L minus 2 to the n, or to the a sub 2, let's say, acting on the ground state, or L minus 3 to the a sub 3, times L minus 2 to the a sub 2 acting on the ground state, and so on. We can make a product of Virasoro generators acting on the ground state. That'll give an energy that'll be minus k plus 2a2 plus 3a3, and so on. Of course, to make finite energy states, we should only create states by acting with finitely many ln's. for any given state. So what has been written here, I've simply written down a generating function that counts these states. So the 1 over 1 minus q squared, well, this is like a free Bose gas. The grounded energy is minus k. The excitation energies are 2 times an occupation number A2, 3 times an occupation number A3, and so on. It's a one-dimensional Bose gas, except the lowest momentum is 2. The allowed energies are 2, 3, 4, and so on. And this is simply the partition function of the free Bose gas. So what I've written is the partition function that counts all the states we know about that are close to the vacuum and that were essentially, whose existence follows from the construction of Brown and Hanel. Now, although it's a nice function, it can't be the full answer because it's not modular invariant. Modular invariance is a special case of general coordinate invariance that exchanges the space direction and the time direction. When we go to Euclidean signature, we should be able to exchange space and time, a 90-degree rotation, so to speak. And that gives what should be a symmetry of the partition function, but this particular function isn't modular invariant. So there have to be some additional states, which in the lingo means there have to be some additional primary fields other than the identity. And the partition function is not going to be the function we wrote. It'll begin that way because near the vacuum, Brown and Hanel already described all the lying excitations of the vacuum. So it will begin this way, but at some point there will be more states. And we're going to interpret the fact that the theory is classically trivial to mean we should make L as large as possible. As far as the near anti-de Sitter space, there was nothing except these states. We have to add something else, but we're going to push it up as far as we can. It turns out that the largest you can make L is k plus 1, and if this is the right value, then the partition function is uniquely determined. And my proposal is that this gives the partition function of the dual conformal field theory, including the black holes. Now, I want to explain this statement that if L is as big as it can be, then there's a unique possible partition function. A Riemann surface of genus 1, they're parameterized by something called the J function. Well, a Riemann surface of genus 1 is made by taking a parallelogram and identifying opposite sides. And one starts with a complex number tau on the upper half plane, such that the corners of the parallelogram are at 0, 1, tau, and 1 plus tau. Modular invariance, by the way, acts like so, where A, B, D, and C are integers, and exchanges different ways of parameterizing essentially the same torus. Then it's convenient. So Riemann surfaces of genus 1 are parameterized by tau up to a modular transformation. But there's another classical way to parameterize it. We introduce Q, which is e to the 2 pi I tau. And then there's this magical function of Q, the J function, which has a simple pole at Q equals 0, and then a Laurent expansion around it. So Riemann surfaces of genus 1 are in one-to-one correspondence with values of J. So if you use tau, which is a more obvious way to describe a Riemann surface of genus 1, you have to worry about modular invariance. But if you change variables from tau to J, then modular invariance disappears. The modular invariant information that's contained in tau is no more, no less than the value of J. It's actually slightly more convenient to subtract the constant and let capital J be this function. So, I mean, in the 19th century, this function was constructed, and it was a little bit funny that the coefficients are so big. This one was just a historical artifact. You can change it by subtracting a constant. But you start with this problem that doesn't involve big numbers, which is to eliminate the action of the modular group 1 tau by changing variables to a new variable that contains all the modular invariant information. Let me finish what I'm saying, and then you can interrupt. So the question doesn't involve any big numbers, right? But the answer involved big numbers. It's a little bit like the gauge hierarchy problem. The answer involves a big number, which is the ratio of the Gutt scale or the Planck scale to the W boson mass. But we don't know what's the question that hopefully doesn't have a big number that has an answer that involves a big number. So here, the question was to solve for modular invariance by introducing a modular invariant variable. No big numbers there. But when you solve the problem, out pop big numbers. Forget this one, which can be changed. But this one, we can't modify. J was unique up to adding a constant. So this 196884 is just a fact of life. And the coefficient after it is something like 2 times 10 to the 7. And they grow from there. So big number, it's like this, well, I won't repeat the analogy, but there was a question. If you're sure you need to ask now.
I was just wondering why you're choosing to focus specifically on -1.
Because it's easier. But knowing genus 1 is equivalent to finding the energy levels, but not knowing the interactions. So it's not a complete description of the theory, but diagonalizing the Hamiltonian is a good start. So modular invariance means that the partition function is a function of J. We could say it's a modular invariant function of tau, but it's much easier to say it's a function of J. Now, the partition function actually has a pole at q equals 0 because the ground state has negative energy. Even our approximate partition function had a pole at q equals 0. But there are not supposed to be any other poles because, in general, in conformal field theory, the partition function converges as long as q isn't 0. So the only pole is at q equals 0, which means j equals infinity. So a function of j that's only infinite when j is infinite is otherwise known as a polynomial in j. So the partition function must be, with our assumptions, a polynomial in j. Our assumptions might be wrong, but they lead to the conclusion that the partition function is a polynomial in j. And we can be much more specific. It must be a polynomial in j of order k, because since the ground state energy was minus k, the pole at q equals 0 is of order k. Right? Anti-de Sitter space has energy minus k, and the excitations above it have less negative energy. So the pole is of order k, and therefore the partition function is a polynomial in j of order k. So it's determined by k plus 1 coefficients a sub r. It can be written like this. And we can solve for all the energy levels if we're given k plus 1 numbers a sub r. I told you that holomorphic factorization was a drastic simplification, and here it is. We can find all the energy levels and multiplicities in terms of k plus 1 unknown numbers. Now we can, for example, we can pick these coefficients to make z of q agree with the naive function up to and including the term of order q to the 0. They are precisely k plus 1 coefficients between q to the minus k and q to the 0. And if we ask to get this function up to terms that vanish at q equals 0, then the a's are uniquely determined. And since they're uniquely determined, we have no control over the term of order q. It's above the ground state by k plus 1 units. So there will be primary fields of dimension k plus 1. Well, we interpret them as black holes since the theory is trivial except for the black holes. In fact, something nice happens. The minimum classical black hole mass in these units is k. But the Bekenstein-Hawking entropy vanishes if the mass is precisely k. So classically, black holes of positive entropy exists precisely if the mass is greater than k, which is in perfect accord with the fact that, according to our proposal, the lowest dimension of a primary other than the identity is k plus 1. We didn't put in the minimum mass of a black hole, but we kind of got it out with a little sleight of hand. And the partition function that I've described how to calculate, though I didn't really write down a formula, gives a result for black hole degeneracies that agrees perfectly with the Bekenstein-Hawking entropy. This may sound like a miracle, but it wouldn't be if you're familiar with the fairy tale of Dijkgraaf, Montesano, Moore, and Verlinde. Just for fun, if k is 1, the partition function is the j function itself, and the number of states at mass level 2 is therefore 196884, and one of them is the stress tensor, or I should say one state corresponds to an operator, which is the stress tensor. So the other 196883 states are primaries of dimension 2. And the black hole entropy is therefore the logarithm of 196883, which is 12.19 approximately, while the classical entropy of a black hole with k equals 1 and mass 2 is 4 pi, which is about 12.57. So we're only off by a little bit, and it gets better from there. If you increase k and the black hole mass, it quickly improves. After all, this is the case that is worst. The Bekenstein-Hawking approximation that we've used here is an approximation when the radius of curvature and the black hole Schwarzschild radius are both much bigger than the Planck length. But by taking k and the mass to be as small as possible, we've gone as far as possible from the classical limit. So this is really the worst we're going to do, and it will only get better from there as we approach the classical limit. But let's go back to k equals 1. The number 196883 is a very special number. Back in the 70s, the last of the sporadic or exceptional finite simple groups was constructed, the so-called monster. The lowest dimension of an irreducible representation of the monster is 196883. It was John Mackay who noticed that this is very close to the coefficient of the third term in that 19th century function, the j function. And soon it was discovered that higher coefficients of the j function are similarly related to the monster. And Frank, Lopowski, and Merman constructed, well, first conjectured and then constructed, a holomorphic conformal field theory whose partition function is our friend capital J. They also conjectured that their theory is the unique holomorphic CFT with this partition function. If that's right, and if holomorphic factorization is also correct, then the Frank-Lopowski-Merman monster theory must be the right one at k equals 1. Well, I mean, if c equals 24 or k equals 1 is a valid value for quantum gravity, and if holomorphic factorization holds, that second one is a big if, perhaps, then the Frank-Lopowski-Merman theory must be the right one. So we can interpret the monster group as the symmetry of 2+1-dimensional black holes, at least at this value of k. What about higher values? Well, it's not hard to show that the coefficients in the Q expansion of the partition function can always be expressed in terms of monster dimensions. So it's conceivable that the monster is a symmetry of 2+1-dimensional quantum gravity at every value of k. But I don't know how to show that this is true, or that CFTs with the claimed partition functions do exist. Incidentally, if they do exist, then they're almost surely dual to pure gravity, since what else can they be dual to? We made sure they had nothing except anti-de Sitter space, the Brown-Hino spectrum, and black holes. So, if they exist, they'd be dual to pure gravity, not to something else. There's a close analog of this in the supersymmetric case. The allowed values of the central charge are 12K, roughly speaking. There's a little sleight of hand that you can read about in the paper. Again, you can more or less uniquely determine the partition function by similar reasoning. And there are candidates for the right theories if K is 1 or 2 in this case. The K equals 1 theory was again constructed by Frank, Lopowski, and Merman, and understood more recently by a student of Frankel's, John Duncan, only recently, while the k equals 2 theory was constructed by Dixon, Ginsburg, and Harvey by making a twist, so to speak, of the original FLM construction. The k equals 1 and k equals 2 theories have in common a discrete symmetry group that's smaller than the monster, but is again one of these sporadic finite groups, the Conway group. Well, I should have scrubbed the sentence. There's some speculations, but improved from this remark in my paper. So I guess I'm going to let you off the hook a little early today because I know you've been grossly overworked this week. Thank you. Yes?
You mentioned the black holes as the only non-trivial objects. Couldn't there be wormholes, other objects?
Wormholes, well, in general relativity in general, wormholes are behind black hole horizons. So there are solutions that have wormholes, but actually from the outside they look like BTC black holes. What's that? From the outside, you can't differentiate. Now, it's not clear what it means that there are wormholes behind the horizon. Alex Mahoney, actually, one of our members, has tried to interpret the microstates of the black hole in terms of quantization of the phase space of the wormholes. And there might be some truth in that. But at any rate, from this point of view, the wormholes are just black holes. That's true in general relativity in general, by the way. Yes, Michael?
Sorry, there's a very stupid point that I'm missing, which is very appreciated. Normally, in conformal field theory, you have a holomorphic and an anti-holomorphic side.
Yes.
Characters.
Right.
Only the sum of the characters is Montreal invariant. Here you're working with a single holomorphic Montreal invariant object. Can you defend that?
Well, first of all, it's in general worse than you said. You describe what's called rational conformal field theory. There's the holomorphic one with one left and one right moving characters. There's a situation you described with finite characters of both kinds. And there's the generic situation which has no factorization at all. It has left and right moving Virasoro. So a priori quantum gravity in 3 dimensions could be one of those 3. I aim for holomorphic factorization because it's by far the simplest hypothesis, and I feel that a theory that's said to be said to be trivial ought to be simple. So I tried to guess what its simplicity was. I may have guessed wrong. But I did one little calculation that supported it, which was I took the gauge theory description at face value, and it gave that k left and k right were multiples of 24, and those were the values where my hypothesis was possible. Okay, so I could have gotten a different answer, and I would have, well, if the answer had been sufficiently different, I would have known that the hypothesis was wrong. Finally, there was one little bit of positive feedback, which was that the black hole threshold was natural. We didn't really put in the minimum mass of the black hole, but it came out, you could say. But you could also claim, by virtue of other things known about black holes and modular invariants in 3 dimensions, that that isn't really an independent check. You might want to look at the fairy tale paper to form more of an opinion on that. So, I don't promise it's right. Yes?
So can you say a little more about what I know about holomorphic CFT at higher value of k?
About what the theory would be at higher values of k?
Yeah, are there examples of holomorphic CFT?
Well, there are all kinds of examples of holomorphic CFTs at higher values of k. But we need a lot more than that. We need what's sometimes called an extremal CFT, where there are no primaries up to dimension k plus 1.
Yes.
And there aren't examples of that which are known above k equals 1. That's the crucial ingredient. The way you asked the question, which was just for holomorphic CFTs at higher values of k, you made it too easy. There are bucket loads of those. One thing I'll say is that there is a paper that appeared on the web a few days ago by Yi and Gayato, who showed what's the genus 2 partition function at k equals 2 or 3. if the theory exists. So that might make it seem a little bit more tangible. A lot of nice formulas, and they kind of work miraculously. It's a pity if the theories don't exist. Yes?
It wasn't very clear to me if you have renormalization for the cosmological constant in the Chern Simons.
No. The cosmological constant is, in SU2 gauge theory, the commutator of T plus with T minus is 2 times T3, and that number 2 is not renormalized.
But it's because it's like constant, structural constant of the
Yes, right. The cosmological constant here plays a role analogous to the 2. And Newton's constant isn't renormalized because it turns into a Chern Simons coupling. And in general, Chern Simons couplings aren't renormalized, roughly speaking. What the statement means is that they're not subject to infinite renormalization. If you want to express a physical observable in terms of the Chern Simons coupling, the classical formulas are not exact. That's sometimes described for some purposes as a finite renormalization. It's a different meaning, however, of the word renormalization. Yes?
In the past, people proposed fluid theory as to history. What do you think of that proposal?
Well, it contradicts the fact that the theory has anti-de Sitter space. Anti-de Sitter space, one of the most important things I said, hopefully sounded trivial when I said it. It was aimed to sound trivial. I told you that the theory had a unique stable SL2R invariant vacuum, which had anti-de Sitter space as a classical approximation. If you accepted that one, then the Liouville theory is wrong, because Liouville theory doesn't have an SL2R invariant vacuum. And incidentally, although people often say loosely that Liouville theory is wrong because it gives too small a black hole entropy, the actual answer really is that Liouville theory gives an infinite black hole entropy because of the Liouville zero mode. Liouville theory, unfortunately your question was one for connoisseurs. So I probably shouldn't be answering it in detail. But Liouville theory doesn't have enough oscillators to make the Bekenstein-Hawking entropy, but it has a zero mode with a nasty continuous spectrum above a certain threshold. And the continuous spectrum means that the entropy is infinite. So Liouville theory is maximally, well, I can't promise that a quantum theory corresponding to 2+1-dimensional pure gravity exists. And if it exists, I can't promise it has that it's a good model of black holes. For example, it could have long strings that Natty and I studied in a different context. And then the entropy would be infinite, and the spectrum would be continuous above a certain threshold. My hypothesis at the beginning was that the theory describes anti-de Sitter space and small fluctuations around it, and black holes with the Bekenstein-Hawking entropy. So Liouville theory is maximally bad from that point of view. It would get each of those statements wrong. It still has a lot of adherents in the wider world, though. There are a lot of people out there who think that all my statements... Okay, go ahead.
Do you have black hole with angular momentum?
Yes. Well, we get them, you see, I described the left moving part. Angular momentum is the difference between the energy of the left movers and the energy of the right movers. There's no reason for those two energies to be equal. Yes?
I'm not sure how would you rigorously determine the right value of L over C?
Definitely not. No rigor there. I was hoping to get the answer 24, multiples of 24, because to make the theory as simple as it could be. And gauge theory does make the value 24 natural, but even so, there's some slightly subtle choices you could make. They're explained in the paper. I don't want to go into it now. But using gauge, more fundamentally though, using gauge theory to settle the question is completely non-rigorous. It's the only thing I could think of to do. No one else has made another suggestion. Seriously, I don't know if I found the right values of K, of C, L over G. I'd be happy to hear another suggestion. I told you up to what point the lecture was correct. I don't make any promises about any statement after that. Yes?
Something, I understand. So you have these left numbers and right numbers.
Yes.
And you multiply them together.
Yes.
And say, let's assume that we don't have the Chern Simons, so just pure gravity without the Chern Simons to the gravity
Yes.
description. So now we go to large K and large level. And we have some mass, and we have many different angular momentum.
Yes.
Do all of these classical solutions, are they known?
Almost. There's a slight embarrassment. But roughly speaking, they correspond to spinning black holes. But when you say all these solutions, sorry, these are quantum microstates. The idea would be that they're the classical description of the black hole only sees the mass and angular momentum, which would essentially be the energies for the left and right movers. The counting of quantum states agrees with the Bekenstein-Hawking entropy, but, well, loosely speaking, there's no known way to see classically where the microstates come from. There is this suggestion by Maloney that I mentioned before about the wormholes behind the horizon. I don't know if it works. I don't know if I answered whatever question, if I interpreted the question properly.
I was asking about given value of the mass, there are different values of the spin, which are predicted by saying that the answer.
Loosely, there's a subtlety, but loosely speaking, all values of the spin occur in the classical theory. Because the black hole can have any angular momentum. Well, at least temporarily we're out of questions, so maybe we should call it a day. I'll still be around tomorrow if you want to ask any more.